Hello everyone, this is our presentation for group project which is 2's complement with hexadecimal, and this is our group members. This is Zul Hakim, this is Tong Ming, and this is Saharul. So first we are going to do the demo of the program. Now we run the program. So first thing, the program prompt the user to enter the input, and we will enter the input as follows. Okay, so then the program print the next prompt alongside with the input value and also the 2's complement of it, and the program will ask us whether to repeat the program, and we will repeat because we want to check the first 2 complement. So we put the 2's complement value from before, and as we can see here, the value is the same as the first input, which means the 2's complement conversion is correct. So again, we are going to repeat the program, but this time we will put the wrong input, okay, which is the program will tell us that the input is error. Okay, and to stop the program, we just input and then the program will stop. So here's how the code goes. Okay, this is our string and variable. Okay, next from the start here, which start part is the part where the program print the first prompt for the user. Then here is the get input. Okay, the user will enter the input, and starting from this line, okay, it will print the next prompt alongside with the original input value, and then until last line over here, it will jump to the error check, okay, to check whether the input is correct or not, to print the 2's complement value.
So after get input, we'll move to part error check, where we must make sure that all 4 character inputs are valid. So for part error check, we will check for digit inputs, which is character 0 to 9, and we'll do conditional jumps for uppercase and lowercase letter inputs. So firstly, we'll move the value from ESI address, which is from array num hex, into our AL. And then we compare our AL with 39H and 30H, which is character digit 9 and character digit 0. So if the input is above 39H, that means that our input has a high probability that it is an uppercase letter or a lowercase letter. So we'll jump to uppercase for the next checking. If it is below 30H, that means it is an invalid input. So we'll display error message. If not, we'll just jump to valid input for the next process. In part uppercase, we'll check for uppercase letter inputs. So we compare our AL with 41H and 46H, which is character uppercase A to character uppercase F. If it is below 41H, that means it is an invalid input, so we will display error message. If it is above 46H, it has probability that the input is a lowercase letter input, so we will jump to lowercase for next checking. If not, we will just jump to valid input for next process. In part lowercase, we will check for valid inputs lowercase a to lowercase f. So we compare the AL with 61H and 66H. If it is below 61H or above 66H, that means it is an invalid input, so we display error message. Okay, next, moving on to our next part, which is the valid input part. This is where we'll change our character inputs from a character value into its corresponding integer value. Let's say if I input the 4 characters to be uppercase A, 0, uppercase B, and lowercase c. For the first character, uppercase A, which is equivalent to 41 hexadecimal, we'll first subtract it with 30H, which becomes 11H now. Then we compare the AL 11H with 9H. If it is less than or equal to, we'll move to the next bit for the 2's complement process, but 11 is larger than 9H. So we continue subtracting the AL with 7H, 11 subtract with 7H, the value becomes 0AH, and then we subtract again with 20H. So 0AH minus 20H, we'll get final value of AL equals to EAH. For the next character, which is 0, character 0, equivalent to 30 hexadecimal, we'll subtract it with 30 hexadecimal. So 30 subtract with 30, it becomes 0H. And we compare with AL 09H. So 0 is less than 9, so we'll jump to next bit for the 2's complement process. For our third character, which is uppercase B, equivalent to 42H, we first minus 30H, equivalent to 12H, and then 12H again. It is larger than 9H, so we continue subtract the AL 12H with 7H. So 12 minus 7 equals to 0BH, and then subtract again 20H, it becomes EBH. For the last character, character lowercase c, which is equivalent to 63H. We first subtract with 30H, equivalent to 33H, and then we compare it with 9. So 33H is larger than 9. So we'll continuing subtract it with 7H, which is equivalent to 2CH, and then we subtract 20H again, which is final value of AL equivalent to 0CH. So moving on to our next part, which is the next big part, this is where we'll do our 2's complement process. So firstly, we move the value of AL, let's say character uppercase A, when if we calculated from value input, the final value of AL becomes EAH or 11101010 in binary into the ESI address to store in the array num hex. Then we'll repeat this process for the next 3 characters. So now we'll move our value of num hex, which is 11101010 in binary into our DH, and then we'll move value 4 into our CL. Next, we shift our DH to the left by value CL, which is by 4 bits. So now our DH will becomes 10100000 in binary. Then we'll move our num hex plus 1, which is the second character, which is character 0, and after calculating value input, the value AL becomes 0H into our DL. So DL becomes 00000000 in binary. Then we'll add the value of DH, which is 10100000 with DL, which is 0H. So DH remains the same, 10100000. Next, we move num hex 2, which is character uppercase B, and calculated from value input, the final value AL becomes EBH, or equivalent to 11101011 in binary. So this value is moved into DL, and again we shift the value of DL by 4 bits to the left. So now our value of DL will be equals to 10110000. And finally, we'll move our fourth character, which is lowercase c, and after calculating value input, the final AL value becomes 0CH, or equivalent to 00001100 in binary. So we'll move this value into our BL, and we'll add the value of DL, which is 10110000 with BL, and finally our DL becomes 10111100. So you can see here, our DH has 8 bits, DL also has 8 bits. So if we combine DH with DL, we'll get the value DX in 16 bits. So for this DX, we'll do the NOT operation, which is equivalent to our bit flipping process in the 2's complement. So after the NOT operation, our final value of DX will become 01011111 01000011 in binary, and finally we'll add 1 into our DX to complete the 2's complement process, and our final value of DX now becomes 01011111 01000100 in binary. And if we convert it into hexadecimal, it will be equivalent to 5F44, which is the correct value. So this value 5F44 will convert it back to its corresponding character value, which we will then display in the output.
The codes afterward are simply used to print the second complement number into the terminal. First, the program clears the unnecessary bits. Then, it compares whether AL is less or equal to 9 hexa. If no, we add 7 hexa to AL. If yes, we proceed to loop 1. Here, the program adds AL with 30 hexa so that it will be able to print the character. This process repeats until the program successfully prints all the 4 characters. Then the program will prompt the user if the user wants to repeat the program or not.
That's all from us. Thank you.